So last time we have studied the fundamental theorem of arithmetic, which states that every integer n greater than 1 can be expressed as a product of primes. Either the integer itself prime or the integer, if it is composite, then it can be factored into primes in unique way. And now we shall consider a corollary for the result as the integer can be expressed in canonical form. Every integer n greater than 1 can be expressed uniquely in canonical form. Or what is the canonical form that we shall see as n is equal to p1 raised to k1, p2 to the power k2, and so on, pr to the power kr, where p1, p2 etc. are primes. K1, K2, Kr are positive integers, primes, and these primes are such that these are arranged in order. P1 is less than, P2 is less than, so on up to Pr. Increasing order these are arranged, and Ki are positive integers. We may say positive or non-negative integers, maybe 0 or non-negative integers. For example, we can consider as suppose 360, and this 360 can be written as, we can factorize it as first as 36 into 10, then this may be written as 6 into 6 into 2 into 5, or further 6 is 2 into 3, and thus this is 2 into 3, 2 into 3 into 2 into 5. Now you may observe how many distinct primes are there, 2, 3 and 5, but 2 is repeated 3 times. So we collect the powers of 2 and write 2 to the power 3. 3 is repeated 2 times, so this is 3 square, and 5 is repeated once only, and thus the canonical form of 360 is 2 cube, 3 square and 5 to the power 1. So this is written in the same form, p1 raised to k1. Here p1 is 3, k1 is p1 is 2, k1 is 3, p2 is 3, k2 is 2, and p3 is 5, and k3 is 1. So this form is known as the canonical form of integers. Now another example can be considered as second, 756. This is divisible by now 2, and therefore we can write, so it is also divisible by 3. So 3 into, say the divisor first is 2, then may check it. Yes, and then this is 3, this is divisible by 2, and we will get 1, then 2 and 6, and further 3 into 2, again this is divisible by 3, so that is 3 into 2 into 3, and 42, 2 into 21, or this is 3 into 2 into 3 into 2 into this is divisible by 3, 3 into 7. Or finally we shall see what are the primes, 2, 3 and 7. So 2 repeated 2 times, so we can write 2 square, 3 repeated 3 times, so this may be written as 3 to the power 3, and 7 repeated once, so 7 to the power 1. So this is the canonical form of 756. Now this canonical form is useful to obtain the greatest common divisor of two integers. Now how it can be done, that we shall see. So we can write this as a remark. So this is the canonical form of 360. Let A is equal to, say, primes we shall consider the same, P1 raised to K1, P2 raised to K2, and so on, PR raised to KR, and B. A and B are expressed in the same primes. That means these primes either divide A or B, and therefore, but the powers may be different. P1 raised to J suffix 1, P2 raised to J2, and so on, PR raised to JR. So this is the expression with exponent may be 0. And let further Li is minimum of Ki and Ji. So powers, minimum power we shall consider. Li is minimum of Ki, J, minimum of these powers or exponents. L1 will be minimum of K1 and J1, L2 will be minimum of K2 and J2, and in this form. Then GCD of AB is equal to P1 raised to L1, P2 raised to L2, and so on, PR raised to LR. So what is the meaning of this, that we shall see. For example, we have these earlier numbers. 360 in canonical form is 2 cube 3 square 5 raised to 1, and another number we have considered is 756. So 756 is having the expression 2 cube 3 cube 2 square it is. So 3 cube into 7 to the power 1. But we have to express these two numbers in the form of same primes. Here see P1, P2, PR, P1 up to PR. The primes are the same, powers may be different. But you may see here the primes are not the same, 2, 3, 5 and here 2, 3, 7. But we can consider 7 here with 0 exponent and 5 here with 0 exponent. That means this I shall write 2 cube 3 square 5 raised to 1, and 7 is not there, but we can write 7 with 0 exponent because 7 raised to 0 is 1. And this also we can write 2 square 3 cube 5 we should write with 0 power. In canonical form the order is important. We have 7 was not there, but we have written 7 with 0 exponent. 5 is not there, but we have written 5 with 0 exponent, and 7 as it is. So you note this. Now this is in the same form. P1, P2 up to PR, P1, P2 the same primes 2, 3, 5, 7, 2, 3, 5, 7. So this can be done for any two integers A and B. If a few primes divide either A or B. And now what we have to consider, Li is minimum of the power. Now GCD of 360 and 756. Therefore, GCD of 360, 756 is equal to 2 to the power L1 means from this minimum of K1 and J1. So L1 is now you see minimum of 3 and 2. What is minimum of 3 and 2 is 2, and 3 to the power. What is the minimum of the exponent of 3 are 2 and 3, again 2. 5, and see the power of 5 or exponent of 5, minimum of 1 and 0, which is 0. and 7 to the power. Again you see the exponent of 7, 0 and 1, minimum of 0 and 1 is again 0. Now we can write this is equal to, so it is 4 and this is 9, 4 into 9, 36. So this is the GCD of 360 and 756. You can check this using the Euclidean algorithm, that we have solved the problems to find a GCD of two numbers. So this is the use of canonical form. Any integer can be written in canonical form, and from the canonical form we can find out GCD. But in general, we should use Euclidean algorithm, not this method, because this is actually lengthy. So these are not so much big integers, therefore we have factored earlier. But for bigger integers we have to use Euclidean algorithm. That means we have to divide the bigger number by smaller, and then consider the same procedure. Last non-zero remainder is the greatest common divisor. So that procedure you should use. Now we shall consider a theorem which is due to Pythagoras. As this is our theorem 3 in this chapter, and this theorem was stated and proved by Pythagoras, famous mathematicians. The number root 2 is irrational. This is the theorem stated by Pythagoras. Pythagoras actually was a group of mathematicians, and they studied geometry also and number theory also. In geometry we know the Pythagoras theorem for right angle triangle. Sum of squares of two sides is equal to the square of hypotenuse. And here the theorem is for this number root 2 is irrational. Now this can be proved in two ways. We shall use one method of that as indirect, it is indirect method. Suppose on the contrary root 2 is rational number. On the contrary means opposite result we are assuming, root 2 is rational. And we know by definition of rational number, a rational number can be expressed as quotient form a upon b. So therefore let root 2 is equal to a divided by b, where the GCD of a and b is 1, or we may refer this as 1, where the GCD or GCD of AB is equal to 1. This can be done. Now if you have a number in this form, say 4 by 6, then GCD of 4 by 6 is not 1, but this can be reduced. This can be written as equal to 2/3, and now the GCD of 2 and 3 is 1. So the number should be written in shortest form. That is the meaning, GCD of AB is equal to 1. But by the theorem on greatest common divisor of two integers can be expressed as combination of linear combination of two numbers a and b. So therefore there exist integers r and s such that 1 is equal to AR plus BS, because 1 is greatest common divisor of A and B, and we have proved this theorem in first chapter. The greatest common divisor, whatever it may be, if it is D, then that D can be written as AX plus BY. Instead of X and Y, we have used R and S letters. So 1 is equal to AR plus BS. Now we consider root 2. So root 2 is equal to root 2 into 1. and this now can be written as root 2, 1 is AR plus BS, or further this is equal to, left side is root 2, right side is root 2 into A into R plus root 2 into B into S. Just we have multiplied, and now we use this first result. So this is equal to, what is A value from this? Root 2 into B, and put it here. So root 2 into B, that is 2B. So this will be 2BR plus, and now what is root 2 into B? Root 2 into B is only A. So there plus AS. Here we have used by the first result, or this relation. Root 2 is equal to A by B. We have assumed it. Rational means it has this form. And now what this says? The RHS of this AB and RS are integers. Here these are integers, and we have R and S are integers, or here we can express where A and B are integers. Such that GCD of AB is equal to 1. And now you see AB are integers, RS are integers, and therefore the product of integer is integer, the sum of integers is also integer, and that means the right side is an integer, but the left side is root 2. So this what the result says, root 2 is an integer, and that is a contradiction. So root 2 cannot be integer. The right side, the RHS of this is an integer, and therefore root 2 will be integer, and therefore root 2 is an integer. This is a contradiction, and thus this contradiction arrived due to our supposition. What we have supposed is root 2 is rational, and that is wrong, and therefore we must have root 2 is irrational, or root 2 is an irrational number, and this completes the proof. So thus it is a simple result. The number root 2 is irrational, proved with the help of this greatest common divisor is 1. And this is about the theorems on from this chapter. Now we shall consider example. Now see, it is from problem set. We will consider one problem as prove that any prime of the form (3p plus 1) is also of the form (6m plus 1). Now the solution for this, or we may consider any prime of the form 3n plus 1. P may be used, but P is reserved for primes. We use P for prime, and general integers we will denote by m, n, a, b, x, y, etc. P and q we use for primes. So any prime of this form 3n plus 1. What is the meaning of 3n plus 1? Prime in the form 3n plus 1. N is integer. We consider positive integer only. N will have the values starting with 1, 2, 3, etc. But which values will give primes? If n is equal to 1, then 3 plus 1 is not a prime. But if you see n is equal to 2, then this will be 7. Suppose this is p is 7. N is equal to 3, this is not prime, but for n is equal to 4, primes we have to select only, not all, and any prime of this form 3n plus 1. So what are the primes of the form? 7 is a prime of this form where n is equal to 2. Now n is equal to 4, so what this gives? P is equal to 3 into 4, 12 plus 1, that is 13. 13 is prime of this form. So those primes only of the form 3n plus 1. And if n is equal to 5, that is not prime. N is equal to 6, that will be a prime. And that prime will be 6 into 3, 18 plus 1, that is 19. And so on, etc. So what the result says that this is also of the form 6m plus 1. Now this 7 can be written as 6 into 1 plus 1, that is 6m plus 1. Now 13 is a prime of this form 3n plus 1, but that 13 can also be written as 6 into 2 plus 1. And 19 can also be written as, you may observe again this is 6 into 3 plus 1, or that means all these are of the form 6m plus 1. These are of the form 3n plus 1 and these are of the form 6m plus 1. So any prime which is of the form 3n plus 1 is also of the form 6m plus 1, that we have to consider. That we have to prove. Let P is equal to 3n plus 1 be a prime. Now here what we shall say that this n is not odd. Why it is not odd? What happens if it is odd? N is odd, then 3n is also odd, and odd plus 1 will be even. And even number which is greater than 2. So here we shall consider this is greater than 2 be a prime. And here n is odd. N is not odd but even. It must be n is even. Because we have to write the reason for this. Because if n is not even, then it must be odd. Because if n is odd, then 3n is odd. Odd into odd is odd integer. So 3n is odd and 3n plus 1 will be even. So an even number greater than 2 cannot be a prime, and that will not be a prime. And this is thus P is not prime. So therefore we must have n is even. And thus in this expression we have stated that n is even. What happens if n is odd? Then we get a contradiction. P is not prime but P must be a prime, and therefore this possibility is not there, and this must be true. N is even. And if n is even, we can write n as multiple of 2. Therefore let n is equal to 2m. Every even integer is written as 2 into some other integer, where m is integer, where m is positive integer. We are considering only positive integers because primes are positive, greater than 1. And if n is equal to 2m, now we may consider p. So therefore p is equal to 3n plus 1, or that is 3 into n is 2m plus 1, or that means it is 6m plus 1. So this is P, and this proves the result. Any prime which is of the form 3n plus 1 is also of the form 6m plus 1, and the examples of this also we have considered earlier. You may verify the prime of this form is also of the form 6m plus 1, and this proves the result. So this is about an example of depending on prime, and remaining part we shall consider next time. So thank you.